Let's start today by talking about chi-square distribution. Again, that's a gamma subdistribution. But what we want to know is we want to know how to use the table in the back of the book for the chi-square distribution and your calculator to calculate probabilities and percentiles. So a chi-square distribution is a subfamily, a subdistribution of gamma, right? This is a gamma distribution. Remember, gamma random variables have two parameters, alpha and beta. The beta is taken to be 2, and the alpha is specified to be little gamma over 2, where little gamma, that's a little gamma there, that funny looking symbol, is taken to be, well, 1 or 2 or 3 or 4, etc., a positive integer. It's called the degrees of freedom. That's just this name. We won't worry about why it's called degrees of freedom. And since little gamma is 1 or 2 or 3 or 4, etc., that means alpha could be a half, or 2 over 2 is 1, or 3 halves, or 4 over 2 is 2, etc. Alpha is an integer multiple of 1/2. We could write down its PDF. That's kind of beside the point. How do you calculate probabilities with a chi-square distribution? Like, what's the probability that a chi-square distribution specified by its degrees of freedom? And it's somewhat traditional to put the degrees of freedom as a subscript here, maybe with 10 degrees of freedom. DF is 10, that is the little gamma. Again, this funny looking symbol, I should maybe make a little bit more like that, is a lowercase Greek letter gamma. What's the probability that that's, say, less than or equal to, oh, I don't know, 7.3? Just to pick something. With the calculator, and this looks like x squared, but you say chi. C-H-I, don't say chai, say chi, Greek letter chi. With the calculator, go to your distribution menu, go down to chi-squared CDF right there. Lower is always 0, upper in this case is 7.3. DF, that stands for degrees of freedom, little gamma is 10. Paste it. This is going to give us this probability. It's a CDF value because of the less than or equal to. It's about 0.303. Area-wise, what does the graph of a chi-squared probability density function look like? It has this kind of shape. And if this area, this probability is fairly small, that must mean that on this scale, 7.3 might be perhaps right about here or so, for this area to only be 0.303. So this would be a chi-square distribution with 10 degrees of freedom. It's PDF. And we've just found that area to be about 0.303. If we're going to use the table in the back of the book here, we can't get a very, very precise probability. We can only get a range of possibilities. So the table in the back of the book, it's table 4 in Appendix A. It's drawn to look kind of like a bell curve, but it's not really a bell curve. It is right skewed, though it's hard to tell looking at that. The little gamma is this column. We're looking for 10 degrees of freedom. You can see what's shaded is a CDF value. It's an area to the left of a number. The numbers in the table here are not probabilities. It's the numbers across the top that are probabilities. So it's different than a normal table. Where's 7.3 on this line? It's nowhere to be found. That's to be expected. It's a limited number of numbers in this table, but it is between these two numbers. It's between 6.74 and 9.34, implying that the probability that we're after is between 0.25 and 0.5, a very broad range of probabilities there. And this is indeed between 0.25 and 0.5. A bit closer to 0.25. Just like 7.3 is a bit closer to 6.74 than it is to 9.34. So that's how you compute probabilities. If we did a greater than or equal to there, or just a strict greater than, it's a continuous random variable, it wouldn't matter. We would use the complement rule. We'd say it's 1 minus this probability. Something else very important to know, though, is another bit of notation, and this is going to come up on the assignment. Find values along the horizontal axis that are labeled little chi-squared sub something, and the subscript's not going to be the degrees of freedom in this context. It's going to be the area to the right. The area under the curve to the right of that number, like maybe 0.1. Let's pretend this area is 0.1. I haven't really drawn it that way, but just pretend it's 0.1. Well, maybe I should make it 0.2 so it looks a little bit more accurate. That subscript refers to this area to the right. This is similar to the subscript that we used with the z normal random variable, and we said it was an area to the right. It's confusing. It's not a CDF value. It's a complement of a CDF value. It's an area to the right, not an area to the left. This is standard. Unfortunate, but standard. And since this is an area to the right, it also means this would represent an 80th percentile value. The CDF value would be 0.8. And this would be an 80th percentile value for a chi-squared distribution with 10 degrees of freedom. When you use the capital chi-squared symbol for the random variable, the subscript represents the degrees of freedom. When you use a little chi-squared symbol, the subscript represents the area to the right. Going back to the same table, still 10 degrees of freedom, still this line. Remember, these probabilities up here are areas to the left. They're actual percentiles. Since our subscript was 0.2, we're looking for the 80th percentile, which is not there. Okay, let's change it, 0.25. So it's the 75th percentile. 0.75 is there. So that value is 12.5, approximate. It's not exact. 12.5 is what this number is, approximate. Can you find it with the calculator? Yes, though unfortunately there's not an inverse chi-square here. So to find it with the calculator, you'd have to experiment. 10 degrees of freedom, just try different upper values until you get an area close to 0.75. Not quite high enough. We already know the answer is about 12.5. Let's go back and do it again. Plug in 12.5 instead. Oops. It should be pretty close to 0.75. Pretty close. If you want more precision, we could continue fiddling with it. And I'll maybe try 12.52 or something. Just to try it, see how close we get. Getting there. It went up by about 0.0012 there. Maybe if we went up to 12.55, we'd be pretty close. Let's go ahead and try it. Yeah, very close. Table gives 12.5. I know it's hard to tell if they should have ran it at 12.6. We have to go more precise there. To 2 places after the decimal, it's closer to 12.55. Okay, that makes sense. Okay, so you want to be able to calculate probabilities for chi-square distributions. It's actually not a super big deal in this class. We use it, I think, once later on in statistics, but in applied stats, we definitely will use that. So get a little practice with it.